Now the other example we will be looking at would be on simple molecular structures. Covalent substances with simple molecular structures consist of small, discrete molecules that are held together by weak intermolecular forces of attraction. There is a force of attraction between the H2O molecules. Now this force of attraction between uh, the H2O molecules is very weak. Now due to this weak intermolecular force of attraction, which are called the van der Waals force of attraction, the name is, what you call it? Van der Waal. VANDER and WAAL. So there is a very weak van der Waals forces of attraction. What happens is, due to these forces, weak force of attraction, these molecules have very low melting points and low boiling points, because a very small amount of energy is required to overcome the weak intermolecular force of attraction. Now the force of attraction is dependent on molecule size. Substances, for example, which have large molecules, they are held together by stronger intermolecular forces of attraction compared to those with small molecules. If there are larger molecules, there are stronger forces of attraction relatively, and relatively the melting points and boiling points of larger molecules, larger simple molecules, are much higher than those of simple molecules. One thing to remember is that these simple molecules, they do not conduct electricity because they do not have any freely moving charge carriers. Okay, there are no freely moving ions. In water, there are hydrogen atoms, oxygen atoms, there is water molecule, there are a lot of water molecules, there are no freely moving ions, and there is no conduction of electricity. Whereas in larger molecules, covalent substances with giant molecular structures consist of an extensive network of atoms that are held by strong covalent bonds. Like for example, you have let's say diamond and graphite, right? They are allotropes of carbon. Diamond, each carbon atom in diamond is surrounded by 4 carbon atoms. As I mentioned earlier, that due to these large giant molecular structures, they have very high melting points and boiling points. The covalent bond here, the covalent bond between the two adjacent carbon atoms are very strong covalent bonds. In order to break these bonds, you need a very high amount of energy. Therefore, giant molecular structures have very high melting points. Another example I want you to look at is that of another allotrope of carbon, which is of graphite. Here each carbon atom is surrounded by 3 carbon atoms. So for every 1 mole of carbon atom, 1 electron is free, because as carbon is in the which group? It is in the 4th group of the periodic table. So in the last shell there are 4 electrons. So for every let's say carbon atom, if there are only 3 electrons used and 1 is free, so there is 1 electron available per mole of carbon atom which are freely moving. So out of 4, only 3 are used and 1 is free. So if 1 is free for every 1 carbon atom in graphite, so therefore there is a sea of electrons. So graphite is able to conduct electricity, but diamond is not, because for every 1 atom of carbon, all 4 electrons are used in covalent bonds with other carbon atoms. So there are no freely moving electrons. There is no electron available to move freely in order to conduct electricity. Whereas this is for diamond. Whereas for graphite, here, if you look at graphite, the structure of graphite, let's look at it again. The structure of diamond, which is another allotrope of carbon. Each carbon atom has strong covalent bonds with other 4 carbon atoms. So if for every carbon atom there are 4 electrons in the last shell, or 4 electrons are used up, there are no free electrons available for any carbon atom. Now there are no free electrons available in order to mobilize or conduct electricity, so therefore there is no conduction of electricity in diamond. If you again look at the structure of graphite, now we will use the structure of graphite in order to explain that why graphite is so suitable to be used as a lubricant. For every atom of carbon in the structure of graphite, what happens is that these layers of carbon atoms are arranged in hexagons, and graphite therefore consists of many layers of carbon atoms which are held together by weak van der Waals forces of attraction. Now vertically between these layers there are weak van der Waals forces of attraction. Now vertically along the layers there are weak van der Waals forces of attraction. So the layers are able to slide over each other. These layers of carbon atoms can slide past each other, making graphite a soft and slippery substance. Therefore it can be used as a lubricant. Another question which can come into in your exam is that why the graphite and diamond have a very high melting point and boiling point. Remember that both graphite and diamond, they have very high melting point and boiling point because there is a lot of energy required to break the strong covalent bonds holding the carbon atoms together. Both in diamond and in graphite, the bonds between the carbon atoms, this bond and this bond, it's a very strong covalent bond. Due to the formation of a very strong covalent bond, a lot of energy is required to overcome this strength in order to break the bond. So therefore there is a very high melting point and boiling point in graphite and diamond.